In this video, we're going to discuss the rules of inference using propositional logic in discrete mathematics. So before we start talking about the different rules of inference, first let's talk about what our purpose is. Our purpose is to create an argument, or actually a valid argument, where logic will hold. So an argument is just a sequence of propositions propositions like P1, P2, etc., such that if P1 and P2 and P3 and all the way up to Pn, whatever that happens to be, implies, or if then, Q. So we call P1, P2, etc. the premises, and we call Q the conclusion. And if it's a valid argument would mean that the premises imply the conclusion. Essentially, we're saying if this is a tautology, it is a valid argument. So if it is always true, then it is a valid argument. So let's take a look at our statement. If it is raining, I will need an umbrella. Then we say, it is raining. And let's talk about how we might write this using propositions. So let's let it is raining be represented by P. Therefore, this is P. And let's let I will need an umbrella be represented by Q. And here we have an if-then statement, even though I didn't write the N. So let's talk about how we would write this. My first statement says, if P, then Q. My second statement says, it is raining, so that's P. So we know in our first statement, if P, then Q, would mean that if P is true, therefore Q is true. And then I tell you in the second line that P is true. Therefore, what is my conclusion? And again, remember the three dots mean therefore. So therefore, we can say Q is true. I will need an umbrella. What we're going to do over the next several slides is to talk about some of the rules of inference that we'll use for propositional logic. And essentially what we're doing is we're building that toolkit of all of the different rules that we can use to show that the premises imply the conclusion. So the first one is modus ponens, and it's the one we just talked about when it came to raining and umbrellas, etc. And that essentially says that if you have if P then Q, and P is true, therefore Q is true. So we'll keep using that umbrella example. So if it's raining, then I need my umbrella. It is raining, therefore I need my umbrella. Now in order to write this as a tautology, that would be P and if P then Q, or you could have that in the opposite order. And notice that's just these premises. So I'm saying if P is true and if P then Q is true, therefore Q is true. The second one, modus tollens. Very similar, we have if P then Q, but notice now we have not Q. So again, we're saying if it rains, I will need my umbrella. Now it's saying I didn't need my umbrella. So what can I conclude? Therefore, I can conclude it did not rain. A lot of people get confused by this one, but remember we could think of the contrapositive of our original statement and say if P then Q, is the same as writing not Q, then not P. And now if I, oops, I forgot my not Q, not P, then if I say not Q, it's very clear that it's not P as my solution. And again, to look at my corresponding tautology to that one, we have not Q and if P then Q, then not P. So all of these rules that we talk about should have a corresponding tautology. We're going to now look at a couple more rules. The first is the hypothetical syllogism, and this is very similar to the transitive property. The transitive property says if one thing implies another and that thing implies something else, then the first thing implies the last thing. So let's think of it this way. If it rains, then I will need my umbrella. If I need my umbrella, then I should wear galoshes, rain shoes. Therefore, I can conclude that if it rains, I should wear galoshes. So the logic does follow in this case. Again, if we wanted to write that as a tautology, we're just saying if P then Q and if Q then R. If both of those are true, it implies if P then R. The disjunctive syllogism, a little bit different. This one is saying, again, instead of, notice now we have this different sign, so we're not saying if P then Q, we're saying P or Q. So P or Q has occurred, and our next one tells us, hey, not P. So definitely not P. So if it rains, or I need an umbrella, but it didn't rain, then I do need an umbrella. That one doesn't really make sense. But again, keep in mind that it doesn't have to make sense in terms of real life, it just has to make sense in terms of the logic. So I'm either going to eat an apple or a banana, and I didn't eat an apple. Therefore, I ate a banana. So that's what the disjunctive syllogism is all about. And again, we can always write that as the corresponding tautology that says not P and P or Q implies Q. The next two properties we're going to talk about, or rules that we're going to talk about, seem kind of silly, and yet they flow very easily with our logic. So the first one is addition. And addition, notice what I'm saying is P is true. Okay, that's what this first one is saying, is essentially P is true. Notice my conclusion says, therefore, P or Q. So what we know about an or question is that only one of those two needs to be true in order for that or statement to be true. So if they're telling me that P is definitely true, then it makes sense that I could say P or Q is true, because it doesn't really matter if Q is true. I already know that this P is true. So that's what addition is all about. And again, corresponding tautology, we have if P, then P or Q. Simplification is sort of backwards. This one is saying, hey, P and Q have both occurred, and because P and Q have both occurred, therefore I can tell you that Q has occurred, or that Q is true. So it's the same as me, I could just as easily change this Q and say, nope, let's say therefore P. That would still be the same rule, essentially saying, I know they both happened, therefore one of them happened. So again, just kind of make yourself a list of these, keep these in mind moving forward, so as you're working, you can always refer back to these. This corresponding tautology, of course, is if P or Q, then Q, or you could always say if P or Q, then P. Okay, for the last two, we have a conjunction and a resolution. And a conjunction, that terminology should sound familiar to you. Pretty straightforward. This one's saying P is true. This one's saying Q is true. Our conclusion is yes, they are both true. P and Q are true. So we already know that that is a conjunction. We've studied that before. But again, what we're saying is if P and Q are both true statements, that implies, I keep writing Q, that implies P and Q. And our resolution, this one's a little bit harder to get your brain around, but this one is saying if we have not P or R, which means one of these two is true, either this one is true or this one is true, then we have P or Q, and therefore Q or R. So let's talk about the truth values on this one. Let's say P is true, or sorry, not P is true, which means P is false. So if that's the case, then this one could be true or this one could be false. R could be either. But Q has to be true in order for this statement to hold, because remember, one of them has to be true. And again, you could be using T's and F's instead of zeros and ones. It's the same idea. So in this case, this would hold because we know that Q has to be true even if R is false. So let's look at the other option. If not P is false, which means P is true, then R has to be true in order for this first statement to hold, and Q could be true or false, false or true, which means down here this would be true for sure, this one could be either one, and therefore this statement still does hold. So resolution is the last one, and again I can write that as the tautology, not P or R, and P or Q implies Q or R. Wow, sorry for that little V. Okay, so we're going to circle back to where we started when we talked about what is a conclusion, what is a valid conclusion, etc. And what we're starting with here is we're starting with just one proposition. And we have one proposition, and then we have all of the different rules of inference that we just talked about. And we want to end up with Q. So I need to show, starting with P and if P then Q, essentially I want that to imply Q. So what I need to do is I need to essentially build a logical argument. So this is kind of like two-column proofs from back in the day. This would be our premise. Premise meaning, hey, this is given to us right up here. So it's not a property or anything else, it's given to us in the question. From here, I need to continue to use some of the rules of inference that we just talked about. So what if I said P? Well, how can I say P? Well, because here I've got essentially an AND statement, and in an AND statement we know both are true, so this is simplification. That is the rule that we talked about. It was called simplification, and I'm going to put simplification on 1, meaning that I used simplification on statement 1. So P, true. I can also say, oops, P implies Q. And how can I say that? Again, same idea. It's simplification using or on 1. So just like I did before, I'm saying, hey, this is true, this is true. That's simplification on both. And now I can say Q. Well, why can I say Q? Because of modus, ponens using 2 and 3. So remember what modus ponens said? Modus ponens said if we have if P then Q, and P is true, therefore Q is true, and that's exactly what I have right here. So this would be the valid argument that I would come up with to show that the proposition has a conclusion of Q. So let's use that same process, and of course this one is a little bit harder because now instead of having propositions already written for us, now I have to write the propositions myself. So let's take a look at how we might write these, first write these as propositions and or hypotheses, and use those then to determine the conclusion or show that the hypotheses imply the conclusion. So we'll start by looking at the statement, John works hard. And what we want to do is I'm just going to say that P represents that John works hard. And so when I have right now a hypothesis of P, John works hard. Then it says if John works hard, then he isn't having any fun. So if John works hard, and notice this is an if-then statement, if John works hard, then he isn't having any fun. So this isn't means we've got to deal with a negative in there, so we'll get to that. How would I then write all of this together? Well, it's an if-then statement, so I know I'm going to have the implies arrow, the implication. Then it says if John works hard, then he isn't having any fun. So I'm going to say not having fun. Oops, that's a Q. So we'll call John is having fun Q. So if he isn't having any fun, then we say not Q. So it's very important whenever you've got these negatives in there to make sure that you're using the negation. Now let's look at the next statement. It says if John isn't having any fun, so John having fun, we still have the isn't, so now we've got the implication, or sorry, the negation, and we still have an if then, even though there's no then here, it's implied. And then we've got this brand new statement here, he won't make friends, and again that's a negative, so let me redo that. He won't make friends, so making friends would be one of our propositions. And I would then rewrite this as, let's see, if John isn't having any fun, so I've got the if then, and it says if John is not having fun, so again it's a not Q, then not friends, not, and we'll call that R. So I have P, I have if P then not Q, and I have if not Q then not R. So let's go from there and see if we can imply that John will not make friends. So again, John will not make friends would be not R, needs to be our final conclusion. So how do I start this? I'm going to start by saying step number 1 is P. Where does P come from? Well, that's a hypothesis. That's this one right here. Now I've used it. Step 2, I'm going to say we know if P, then not Q. How do I know that? That's also a hypothesis. 3, instead of writing the next hypothesis, I want to say what conclusion can I draw using these two statements. So looking at P, and if P then not Q, then I can certainly say not Q. I'm going to change my color again. I can say not Q. And how do I know that? That's modus ponens using 1 and 2. So yes, there's a not involved, and when we looked at modus ponens, we didn't have a not involved, but it's really the exact same thing. So now what? Now I have not Q, I know is true using modus ponens, and now I'm going to look at if not Q, then not R, and that is a hypothesis given to me, and that is the last of them. So I've used this one already, and now I've used this one. Now what can I say here? Again, using these two statements, I have if not Q, then not R, and then we are given not Q, therefore I can say not R, and I can say that again using modus ponens, using 3 and 4. So now I have used my hypotheses to arrive at the conclusion that I wanted, which was not R. Here's one last practice for us to do together, but what I'd like you to do is see if you can actually work through this one without me. So press pause, try this question out and see how you do, and then press play. So hopefully you took a few minutes to do that. We're going to go ahead and get started going through this together. Remember the end goal, you should keep that in mind all of the time. So let's look at how we might go about solving this, or showing that the premises imply the conclusion. So I'm going to start, and I'm probably going to end up using 2 columns here. I'm going to start saying Q, and Q is a hypothesis. So I really only introduce these as I need them. So I'm introducing that Q is true because they tell me that it's true. Then I'm going to say if Q, then U and T. Oh, I'm going to have to move this over a little bit. So hypothesis here, this is also a hypothesis, and now I've used if Q, then U and T. Because of that, I can use modus ponens on 1 and 2, and I'm just writing it sort of abbreviated so I can fit it all on one screen, but modus ponens would then tell me that U and T is true. I can also say, because of that, because U and T is true, therefore U is true, and T is true, and those are both using the simplification rule, and that is for both. So because U and T is true, U is true and T is true. So now I'm sort of at a standstill, and I'm going to look back up at my hypotheses, and the next hypothesis I might use is if U, then P. And again, that's a hypothesis. Now what I can say is, because I've got U, and if U, then P, therefore I can say P. And how can I say that? Using modus ponens for 4 and 6. And again, writing this very abbreviated. So I'm getting closer, 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 closer. Now I'm looking for something else that I can imply based on what I know. So I have just said P is true, and for this next one I'm going to say P and T. And how am I saying that? Well, because P is true and T is true. And why did I choose to do that? Because over here I've got a P and T, and I needed some way to bring that one into it. So now I can say P and T is true, and that's the conjunction of 5 and 7. So now I'm sure that you can guess that I'm going to use if P and T, then, oops, wrong symbol, sorry. If P and T, then R or S. And again, that's a hypothesis given to me right here. So now I've used all except for not S. We'll get to that one. Therefore, I can conclude that R, sorry, R or S. And how can I conclude that? Again, good old modus ponens, MPP, using 8 and 9. Again, using these two together. So now I'm getting real close, and I've got R or S. And do I know anything about R or S? Well, I know not S. That is a given. It's a hypothesis. And if I know not S, which means S is false, and this is true, R or S is true, well, then I can conclude that R is true. And the reason I can conclude that is the disjunctive syllogism. And that is using 10 and 11. So that one was a longer one, but I wanted to give you one that was a little bit more involved and a little bit harder to do. Next up, we are going to be talking about rules of inference, but we're going to use quantifiers. If you found this video helpful, please like and share.